right, so 1.1, just looking at your book, the very first section is not all that exciting as far as new ideas, because when we went through the driving log, which I did not make a recording for, I apologize, but we kind of did an introduction to a lot of things in calculus. So, but this section is also an introduction to calculus. In our classes at Epiphany, we talked about limits last year and their properties. This whole chapter will be about limits, but this very first section is about what you know right now. So what is calculus based on what you already know? This is probably, I mean, you probably haven't spent that much time reading a calculus book, but this would be a good section to actually read through the chapter. And I did choose this book. So when we changed this book, I had chosen it because I think it's readable. So I do suggest when we go into sections that you read them or go back and look at examples and see what you can follow. Their pictures are going to be way better than mine. 3D shapes look like 3D shapes. I'm pointing at this one down here, that kind of thing. So just keep that in mind. But what this section is good for is talking about what you know from pre-calculus versus what we're going to be able to do with differential calculus. So this is about differential calculus. We talked about that goes with what from the book that you had to read? Subtraction. So we're looking at difference quotient or slope formula, change in y over change in x. So without calculus, we can find the y value. Yeah? Like we could do that in Algebra 1. With differential calculus, we can find the y value that's supposed to be filling this hole. So we call that the limit. So that would be calculus. Slope of a line we can do before calculus. Slope of a curve we need calculus for. And we're going to talk about this today. So the differences between what you knew how to do and what you'll know how to do in calculus, that's what this chart's about. And then they give you another chart that talks about integral calculus, which we talked about being where you add up things. So we had, I don't know if we looked at, did we do some on the calculator, the integral? No? Okay, we might do that today. We'll see. You don't need to know it, but it's fun to look at. So before calculus, you could find the area of a rectangle, right? Duh, we know how to do that. We did that when we were estimating things. But with integral calculus, we'll be able to find things that don't have a specific geometric formula for. So not length times width or volume of a cone. 1/3 pi r squared times h. Those kind of things that have a formula for. Calculus won't have a formula for, but we'll be able to get around that by just figuring out how to do it ourselves. So calculus is a lot of fun that way, at least I think so. But it's also, it makes you think in ways that you'll use in any other aspect of what you're having to do. You have to figure out something. This will help you do that. So surface area of a cylinder, like how much can is needed to make a can of whatever you're going to have in a can. This would be surface area of something that's irregular. So this is the same all the way here. This one is fat here, but skinny here, and then fat again. It has a different kind of shape. This we need calculus for. We will definitely do this one way here at the bottom, which is kind of a cool thing to find volume of definitely irregular kind of solids. Whereas we know how to find this, length times width times height. This is not like that. We won't have a length times width times height. We'll use the idea, but we're going to do something different when we get to integral calculus. All right, so part of this section, when you look at your homework, is just about can you tell the difference between something you would need calculus for and something that you would be able to do on your own without calculus. We are, because it's a double block, we are going to do 2 sections. I'm going to do my best to remember to pause this video when we're done with section 1, so it'll be a separate video. Y'all will help me with that. And then we'll do the second video separately so that I can reuse this next year because, you know, that's my goal. All right, so we're going to start actual notes. 1.1. 1.1 has 2 ideas. One of them is the tangent line problem. That's where we're going to start. The tangent line problem. Is that big enough for y'all? Okay, so the tangent line problem is about, like the picture I showed you a minute ago, where you're trying to find the slope at a point on a curve. So let's take a look at something we could actually figure out slope for. Let's say we have this shape here, and I have an x value here, and I have a point, and I have another point up here. We're going to find not the tangent line. We're not going to start with the tangent line. We're going to work up to that. But in this drawing, I have some shape, and I'm going to look for the average rate of change between this point that's started off, I've started off marking what it's going to be, and this point. So we're going to look first, and I'm going to throw in, I've told you a couple times that notation is huge in this class. I'm going to go ahead and start introducing you to shortcuts or things that are useful in class as far as writing notes, but also I'll try to tell you what things you can use later on your test or not, what everybody in the whole country, might use that would be okay. So average rate of change is what we know how to do right now of change. So that would be if I drew this line here between these 2 points, I would be finding the average rate of change. So you can imagine that if we started here and we're driving a car and then we speed up, it would sort of look like this. So we're pressing the gas pedal and then we press it harder and we go faster, this kind of idea. We could find the average rate of change between this instant and that instant by just drawing a line through the 2 points. And we could do that with, that doesn't say change, now it does, change in y over change in x. And the shortcut to this is pretty obvious. Average rate of change. It's just an acronym, and that you'll see that when I'm too lazy to write average rate of change out, that's what that means. So average rate of change. This is an Algebra 1 idea. We used it in Algebra 2. We used it in pre-calculus. We called it slope. We mainly worked with lines before, but this is what we know how to do before calculus. So let's continue with my picture. If this is x, what is the y value of this point? Like if I name it a point, x comma, what could I call it with this notation so far? I'm not by myself. They're going to warm up. It sounds like I'm crazy. Ben, is this what it sounded like last year? Just me talking and pauses, awkward pauses. Okay, it's awkward pauses. So y'all speak up. What's the y value? How could we write that notation?
Are we estimating it?
No, this is my function, f of x. The dark blue line is f of x. So what could I call the y value? I'll help you out. F of x. How about that? Does that make sense? I have x. I plug it in. I get f of x. I don't know what it is. I'm going to write the general idea for you in this first example, not actual points. I'm actually not going to figure out anything like an answer. I'm just going to represent this symbolically. The other point, in this example, the other value over here is some distance away. It's an added value. So if I start with this being x, this distance right here, I've added something. I'm going to call this one x plus h. And I'm doing this because in pre-calculus, we use this concept and we've already drawn it on the board. So I'm connecting things we know from before. If I call this value here h, just for fun, that means this distance is x and this distance is h. How about that? Does that make sense? Okay. So if this point is my second point, the x value is x plus h. What's the y value? So I take the function f and I plug in x plus h. And that's notationally speaking what I'm looking at. Does that make sense? Mm-hmm. Cool. So how do I find slope of this line, which has a name? The line is called the secant line. Is called the secant line. So as opposed to a tangent line, this is a secant line. A tangent line I haven't drawn yet. A tangent line crosses just once, like it has a touch, right? But doesn't cross twice. A secant line touches 2 times. So how do I find the slope between x and x plus h? My differential, my aka difference quotient. I'm looking for the difference quotient. So I need to subtract the x's over subtract the y's. These pens are so, they fell down all day yesterday. Oh, my fall on my face. I'm not going to do that. Okay, so I'm going to subtract the y's. I'm going to do this like we did last year. I'm going to start with this one so it'll look like what we did last year. F of x plus h minus the other y value, f of x, all over the x value that goes with this y. So I'm going to call it x plus h minus x. So in mine, I've written the blue as 1 point. Yeah, I moved so far. Okay, give up. I have another one. Does it look like the difference quotient? Changing y over changing x? Cool. So that's good. Y'all aren't freaked out yet. So I could simplify that to be f. It's not that much more simple, just a little tiny bit over h. This is the secant line. Now, why is that important? It's important because what happens when I'm going to pause here. Let y'all start writing because I want you to be able to follow. I don't want to lose you. This is like the key to the first semester we have. What happens if I'm trying to find the tangent line at x is if I move this h closer and closer to x. Like this. Let me draw. Can I move this up and draw another? Y'all caught up? All right, so if I said, here's another one, I'm going to draw the same one, just I want to write on it again, so I'm going to draw it again. Here's my x. So my first secant line, oh, my goal is the tangent line, right? That was the title, the tangent line problem. I'm going to draw in the tangent line because it's my goal. I'm going to draw it in black because that's what I have here. This is my goal, right? The tangent line. And the reason it's my goal is because that represents the slope at x. So it's my goal because the tangent line represents the slope at x. And that's what I want. And the problem with it is, what is the problem with it? Why can't I just find the slope at x? What does the difference quotient need to be a difference? It needs 2 things to be able to subtract them. And if I'm just doing a tangent line, which by definition only touches at 1 point, I don't have another point. So here's how we get around that with what we're going to use in limits pretty soon. Originally, my point was up here. That was my h. What if I move it a little bit closer? So my h is now smaller. I'm just going to draw a line. Y'all just have to keep up. There we go. So this blue line is clearly not the same slope as the black line. Clearly not. But what if I move it closer? So it's this dot, and I connect them. This one's closer to the black line. In a second, I'm going to have a lot of blue lines. But I'm going to move it closer and closer, and then so close that it's right here. Am I getting closer and closer as h gets smaller? Does that make sense to you? Can you see, Zach?
It's a glare from that one. You can't see like right
So what we're doing every time is we had an h that was out here, and then we said, what if we moved h over here? And then what if we moved the x plus, so it's really x plus h, right? We made this distance this far, and then now we shortened it, and we shortened it, and we shortened it, and we shortened it, and now we're looking at a dot right here that's x plus h right next to our x. So what we're doing is we're approximating the tangent, which is our goal, with closer secant lines. And when we talked about the infinity principle, we're actually trying to make this distance infinitely small, so small you wouldn't even know there is any distance. We're trying to make h go to what? So small it looks like it's with the line, which means as a number it would be 0. We're trying to make h, it was like 1 away here, and now it's half away, and now it's 0.5, oh, 0.5 is the same, 0.35 away, and then 0.1 away, and now we're trying to make it be x. We're trying to, and this is actually the limit definition of slope, we're trying to make h go to 0. And so 2 things I want you to get out of that is, number 1, you've seen the limit before. Okay, 3 things. Second thing, we can't let h be 0, right? That's like a fundamental math problem. You can't have 0 in the denominator of your fraction. So that's a problem we have to get around. That is the tangent line problem, but I also want you to see that h is not an arbitrary thing that somebody stuck in the bottom of a difference quotient. It came from up here. It came from this, but the x's canceled out. So I don't want you to forget that, because otherwise this seems totally like an arbitrary thing that you're trying to memorize, when all it is y minus y over x minus x. It's just that this x includes the h. Is that in my video? Oh, yeah. So this is where you want to put a giant star or circle it, or find your highlighters that fell on the floor. This is the limit definition of the derivative. The limit definition. Oh, shoot. Definition. I give up. Derivative, and we haven't really defined derivative yet, but that means the slope of a function at any point. Or any x value. So that lets us find the slope of this curvy line here at x, which is what we're looking for. Well, that doesn't show in my video at all. There we go. This original one, that's our goal. Okay, back to here. So the tangent line problem. So way back when, mathematicians were trying to figure out everything. They were trying to understand the moon and the sun and the stars. They were trying to find area of circles. They were trying to find just the distance around a circle. All of that was in Infinite Powers, the book, but curves really stumped them, so they had to figure out how to get around it. And this idea of a limit is how you get around it. The idea that you can have a smaller and smaller, you're going to hear me say this a bunch, we're going to call this infinitely close. Infinitely close. Also, arbitrarily close. Arbitrarily. I'm sorry you have to listen to me spell, but that's how I do that. So those 2 things are about the limit. So we're kind of sneaking up on trying to make it 1 point, even though we require 2 points in order to have slope. So that's the tangent line problem. A little bit clearer? We're going to actually do this a lot as we go forward, but I just want you to know where we're going. Because if we actually figure out limits and we understand that, that's big idea number 1 for calculus. Number 2 is actually the derivative, which we're going to spend a lot more time on derivatives. And once we understand derivatives, we're going to go backwards and use its inverse function, which is the integral. So if the difference quotient is the subtraction, we need its inverse to undo it. We need the addition one, which is the integral. Those are the 3 things we're doing: limits, derivatives, and integrals this year. All right. So questions on difference quotients before we see our other problem, which is the addition part. And we saw this with our velocity graphs that we looked at. So let's look at the second question, second problem. Second problem is the area problem. And the other one was capitalized. I don't know why this one's not. But the problem that mathematicians had was, if you have this kind of graph going on, how are you going to find out the area under a curve? Area under a curve. And we know how to do that. What did we do when we looked at the velocity graphs that we've already seen? What did we do?
We picked up like the shapes that we could easily find area.
So we could find area of rectangles. So we just said, well, what if we made this a rectangle? And we thought of it like that. And then we made a rectangle here, and then we made a rectangle here, and then we had another rectangle. So many rectangles. It would take a while, yeah. So we can do that. We could have found 1, 2, 3, 4, 5, 6, 7. That's what I've drawn in here. 7 rectangles, and they look pretty close to my curve. That'd be a pretty good estimate, right? So how would we get a better estimate? Right? So what we did first was find area of things we know. How do we get a better approximation? Back to that infinity principle. What do we do? What if I had taken this whole thing and magic of an eraser, and I just did this originally?
Bigger boxes.
Is my error bigger here or in the other one? Bigger here. So the other one I did was a closer approximation because I had more rectangles. So I can, just like on this one, I can go infinitely close or arbitrarily close. I can make my, in this case, I have rectangles with rectangles of very, very, very small width. They would be infinitely small. They would be so small that they're basically 0 wide. Can we calculate 0 wide? No. Are we going to approach 0 wide? Yes. Are we going to do it by hand? No. So don't freak out that you're going to have to calculate 100 tiny areas. We're going to figure out how that works, and then calculus takes care of the infinite number of calculations that you would need to do, which is amazing. The notation does that. The idea that the difference quotient and the sum, the opposite of that, are inverses of each other, mean that we can use that to undo functions, and that will help us figure it out. And it was a long time before people were working on these problems separately. The difference, the slope question, the difference, people were working on this problem. Around the same time, other people were working on this problem. And then eventually they figured out they went together, which was kind of interesting. So, and I think this was actually figured out first, even though we're going to do that second. Okay. Yeah. All right, so let's actually do this one with a math problem. We did it with our made up driving records. And I say made up just because that was a like a chart, and it had specific intervals, and we didn't know what happened in between the 5 minutes, right? So we weren't exactly right with the odometer on those problems. But let's do one that we can actually figure out. So I'm going to draw out this function f of x equals x squared. You know what that looks like, but I'm going to draw it only up to 1, okay? So I'm going to have the function kind of looks like this, and I'm going to make this the boundary where x equals 1. So this is 0 up to 1. Everybody knows that's like half of the parabola, right? I could go on the other side, but I don't want to fill up my graph with extra information. So I'm going to calculate the area in this sort of triangular, it's not a triangle, but because it's curved, but triangular looking part. And we're going to do that. We're going to call this approximating area with 4 subdivisions. I'm going to call them rectangles today. And we won't actually really do this until December-ish, depending on, how everything goes. Because I try really hard not to move fast. I don't have a set schedule for exactly when we're going to get somewhere. We're going to get there when y'all are following and memorizing stuff as we go. Because otherwise, moving forward is really awful. So we're going to pick our own pace, and it'll be good. So if I do this with 4 rectangles, and we want to make them equal width, okay? We don't want to randomly pick rectangles out. That would be awkward. There will be some of that, but not obviously first day. So how wide are these rectangles going to be? If I have 4 of them. Imagine I'm drawing 4 rectangles. How wide are they? 0.25. I'm going to use fractions. You can keep the 0.25. They're the same. Whatever floats your boat. I just prefer to use fractions. So I'm going to say this is at 1/4. This is at, I'm going to call it 2/4 just for kicks, and 3/4 and 4/4 just to keep up with how many rectangles I have and that kind of thing. So everybody agrees those are the x values that would be, if I drew lines up and made rectangles, those are the x values. Does that make sense? Okay. So I'm going to use some, this is not really calculus notation, but we use it more in calculus. My change in x, as I go from left to right, each of these widths, this change of x equals 1/4. And that's the width of a rectangle. So I haven't blown anybody's mind yet, right? So I need to draw my rectangles. Now there's 2 ways, actually there's 3 or 4 ways, different ways to do that. We're going to pick 2 ways to look at today. One of them that we're going to start with is going to be the left hand sum. In other words, when I draw a rectangle and I draw it and it goes up, I'm either going to have a height that's calculated from the left or a height that's calculated from the top of the right. So I'm going to have a rectangle drawn in, and this would be the left hand height, and this would be the right hand height. Does that make sense?
Sure.
It will in a second, and if it doesn't, it might on the second go around because we're going to do this twice, once with the left and once with the right. So if I do a left hand sum and I have 4 rectangles, this is what I'm going to have. I'm going to have I'm going to call it height times width instead of length. Is that okay? So I'm going to say height times width plus height times width plus height times width plus height times width. I'm going to have 4 rectangles. And I think for instructional purposes, first time, it's good to just write them out. So the width, I already know. How much is the width? 1/4. So I can actually write right under the width, I'm going to write 1/4. Like, I already know that, so that's nice. I'm going to fill in the height in a second. It's a lot of parentheses, but it's okay. So far, we've divided this space into 4 what's going to be rectangles. And we notice that that means they have a width of 1/4. And we've written out 4 rectangles like this. Now we need to find the height, and we're doing the left-hand height. So the left-hand height for my very first rectangle is going to be in this distance. So like this space is rectangle number 1. And the next space will be rectangle number 2, and then rectangle number 3, and then rectangle number 4. Okay? What's the left-hand height of this first rectangle that's going to be above here? What's the f of 0 here? F of 0. 0. Okay, well that's okay. So this is my first rectangle. It's just flat because I'm taking it from the left-hand height. Now I move to the next rectangle. What's the height at 1/4? What's this point? So it's 1/4 times 1. We're plug it in, right? It's the x value. Here's x. So 1/4 times 1/4 is 1. We're not adding it. We're multiplying it. So 1/16.
So we're not trying to guess it.
We can actually plug it in the function this time. It's not like the one we did with the mileage. We actually know the value of everything because we have the function up here. This is actually 1/2. I just wrote it as 2/4 just to keep them in order. So my next height, so I want to draw this in. I'm sorry. Here's my second rectangle. It has a left-hand height. It's a little bit underneath, but at least it has some height this time. My next rectangle is going to be here in this third vertical space. So I need this dot. What's its height? 1/2 squared. 1/4. So I can draw that rectangle. Do you see how I'm drawing the rectangles with that left-hand height this way? Okay, so this area, I can calculate that area, and I will. It'll be 1/16 when we multiply. And then the last one is going to be this height. So these were the left-hand heights. Left-hand, 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 left-hand height. And so its value is 3/4 squared, or 9/16. So all we've done is add up 4 rectangles. That's it. And then we would take our calculator out and type it in. Oh, I have one here. Y'all can borrow one if you need to. So if you do fractions, I don't have to do the first one at all because it's 0. The second one is going to be 1 divided by 64. 1/64 plus 1/16. 9/64 equals point. So my approximate area under my curve is 0.21875. I'm going to keep it all just for kicks. Did you follow? Okay, let's do this again, but let's do the right hand side. I'm going to draw it again so I can draw everything in there. So give yourself a second to draw it out. I've got 1/4. I'll write 1/2 this time. 3/4. 4/4. 1, 2, 3, 4, 0. So this time, what are we calling this one? If this was the left-hand sum, this is the right-hand sum. You could call it the right sum. You don't have to say right-hand sum. And it's going to have 4 rectangles again. So I'm going to do the same thing I did before. I'm going to write parentheses and then 1/4 plus parentheses 1/4 plus parentheses times 1/4 plus parentheses times 1/4. It's a little bit of overkill, but this step is actually, when we get to FRQs and we need this, we actually do have to write it out. Even if it was a calculator problem, they have to see what you would put in your calculator. So I have to show 4, if they ask me for 4 divisions, I have to show that I added up 4 divisions and I added them. So this is a sum. It's what an integral is. There you go. But this time I'm not doing the left, I'm doing the right. So I don't start with 0. The very first one I start with a 4th. Or sometimes people like to think of it backwards. They actually start on the right and they start with this one. Which would you rather do? Start with a 4th or 4/4? The 4th. Okay, so I'm going to start on this side. This will be my right hand one. And I'm going to plug in 1/4 squared or 1/16. I've already figured that out. That's nice. But my rectangle is different because it's big this time. It's not 0. My second one is going to be, what's the height? This height for 1/2? 1/4. And then I draw that one in, and it's up here. And then I have this guy. So I've got 9/16 and 1. 1 squared is 1. And then we throw all that in the computer. Well, it's a calculator. I don't know why I call it computer. So now I have 1/64 plus 1 divided by 16 plus 9/64. I guess I could have just added 1/4 to the last one because I had 0 in the last one. I've got my approximate area is 0.46875. The difference between these is what? First one's an under, because you see we didn't calculate all these blank spaces. And then this one's an overestimate.
So can you just subtract
What should we do instead?
add them by?
Yeah, let's average them. So we could say I have 2, approximations. It's better than I would just guess off the top of my head. What if I average them and try to say that's better because this is over and this is under, and they should, like this green space, does that fill in here? Kinda, is it close? So we would say, we're going to say 2.21875 plus 0.46875 divided by 2, and plus that guy equals divided by 2, 0.34375. 0.34375. Okay, so this is our approximation. The calculator will be able to tell us exactly. Let's do that. Let's see what that looks like on your calculator. So if you have your calculator, use your calculator. If you don't, watch, we'll do it up here. I'm just going to do it on the calculator instead of using the one over there. I put it in my video, but it's easier for me to type it here. So everybody type in as your y1 x squared. X squared. Got that? Now my standard window is going to have this part so small it's going to be hard to see anything exciting. So let's change our window. Let's zoom in on it. You could either zoom in or you could change your window. I'm going to change mine to be -1 to 2. And then I get it on either side, and -1 to 2 for y as well. And I feel like I have a better, close enough image of what it is.
So you do x squared.
So x squared is our function. That's not the right key. X squared is the function we're looking at.
And then how do we change our window again?
If you hit window, instead of -10 to 10, I've got -1 to 2 from x, and then you skip down to y, and then -1 to 2 again. And I always skip the x scale. I don't really ever change that. Now, where does the calculator do cool stuff for us? Find zeros, find values, find intersections. Where does it do that? You've done all those things. Where's that?
Calc.
Yeah. So we need to find this calc. So we need to use blue and then the trace button to get there. There's two that we've never used before, but we're going to use this year. So tell me about number 6. What does that look like? That looks like slope. Change in y over change in x. Well, d means delta. Exactly. So change in y over change in x. And then the other one is a big, what's called an integral symbol. It looks like kind of an S for sum. So we're going to sum. We're trying to add here. So we're going to use 7. And we're going to, it's going to ask us, the calculator thinks in terms of from here moving this way. So this is the left or the lower sum, lower, it says, oh, limit. The lower number, and then 1 is going to be our higher number. So we're going from 0 to 1. So we're going to type in 0 and enter, and then upper limit is 1. These are the x values. That's why it says x equals.
How do you get there?
And then it makes a pretty shape.
Wait, did you just hit X?
So second, calculate 7.
I did that.
Okay, and then it says lower limit,
Uh-huh.
and you type in 1.
Okay.
And then upper limit, did I say 1? I'm sorry. Second, calculate 7. Okay, so lower limit is 0 up to 1, and then it's already colored in, so it won't color it in again unless you change your window.
So 0 is X. Is Y still 1?
It's not y. It's calculating from the x-axis up to the function, from x equals 1 to x equals 0 to 1. So it's going to calculate the y values, but it wants to know what your bounds are as far as x in the x direction. Now, what did it say? What is the integral of the function that we asked for? Is that close to what we got?
Yeah.
Actual 0.3 repeating. We're really close. So yay. So big ideas. We talked about limit today. We talked about derivative a little bit. We talked about integral, and we actually did one with integral. That's calculus. That's our whole year. That's what we're going to do and get really good at it. Yay. So I have one activity that I want you to do, and I said I was going to pause the video when I was done with this section. So there's homework that's associated with knowing the difference between pre-calculus ideas and what you will need calculus for. And until we can do calculus, we can do things like approximate things. So there's homework associated with that for this section 1.1, and it's posted on Classroom. Okay, bye.